Yeah, thank you very much for this great opportunity to present our work here. What I'm going to talk about today is one aspect about ParityQC, namely our connectivity-aware synthesis. But I would like to also give a little bit a general overview of what the Parity Architecture is and what we are doing at Parity. So I would like to start with somehow the papers that are roughly covered in this talk. And this is also a little bit a summary of the main points that I would like to make, so I'm telling them already in the beginning. So one thing about the Parity architecture that I will present is a paradigm where we start from redundant encoding. So in many codes, the logic is, okay, I have my algorithm, I have my logical qubits, and then after that I add error correction, for example, by a surface code or something like this. In our case, we basically start with the redundant encoding and remove the logical qubits completely. We are only acting in this redundant space. The second important aspect about the Parity architecture is that the interactions become local fields. So this means if I have logical pair interactions, in our code this becomes single qubit operations, and this allows us to mitigate some of the hardware challenges that we usually have, namely that physical interactions have to be done among nearest neighbors. Then I will touch on the parity flow. So this is our mechanism that allows us to actually design the algorithms. What I will show is how we combine or how we make use of physical operations, on the one hand to execute the algorithm, but at the same time to do the logistics of the quantum information on the chip. So this is also often two things that are separate now. So we would do like swap gates or lattice surgery, and on the other hand we have the gates. In our case, we make use of both of them. And lastly, something that we call Parity Twine. I will show you how we can efficiently implement algorithms with that. So let me start a little bit historically, just to get you in the spirit of the parity picture. So this is already quite some old work from 2015, but it somehow shows the logic behind everything that comes after. So imagine you have a spin model which is all-to-all connected. Let's say the blue arrows would be your spins, and your Hamiltonian would look like this. So this is just a problem to introduce the concept. And now you can draw it like this. Now the edges of this graph would be the interactions, and the nodes would be the qubits. Now let's imagine you want to represent this problem not in the original variables, but in the parity variables. So parity variables are simply the product of spins. So for example, if you have pair interactions, it would be pairs of spins. And now in this presentation, I make the product green and with zeros and ones, but these are just qubits like the other ones. So it's just to distinguish them graphically. So if two spins are pointing in the same direction, it will be up or 1. If they're pointing in different direction, it will be down. So this will be the parity. And now from a graph point of view, you would say, yeah, what you've done is something like a dual transformation, right? So you put your information now on the edges instead of the nodes. So every of these qubits would live basically on the edges. And now physically, there is a second aspect, namely, if you would write the Hamiltonian in terms of these new variables, the first thing that you notice is somehow these pair interactions have become single qubit operations, right? Because here you have the product, which means a pair interaction becomes a single qubit operation. And so physically, this is already, I think, the main idea of the whole thing. This is really not just a mathematical transformation, there's really physically something going on. And now, obviously, this cannot be an equation, right? Because if you would just represent every every edge here, you would have too many degrees of freedom. So on the left side here, you have this double sum, which is n times n minus 1/2 elements, but you only have n degrees of freedom, you only have the spins. But on this side, what I call k here is n times n minus 1/2. The whole Hamiltonian has this number of degrees of freedom. So obviously there's a mismatch between degrees of freedom, and in order to make this, so to say, valid, I have to introduce constraints. I have to restrict my space again to the valid space that is physically allowed. And how many of these constraints do I need? So just the number of degrees of freedom that I have to get rid of. So it means k minus n. I have k, I need n, so k minus n constraints. And there's a small subtlety with the +1 because of symmetries in the system. But in principle, it's k minus n. So I can ask myself, can I construct these constraints? And it turns out, yes, I can. I can do this out of closed loops in the original graph. So imagine you cut out a cycle in your graph. Let's take the simplest one, 1, 2, 2, 3, 1, 3. And now we have these two representations, the original logical qubits and the physical parity variables. And in a closed cycle, there's as many of them. No, if the length is 3, there's 3 parity variables or 3 logical qubits. So I can make a truth table between them. And I can, on the left side, write, for example, the logical ones, and on the right side, I write the parity variables. And if I write this full list, then I will find out, that on the left side of this column, there is no closed loops where the number of spin downs is an odd number. And the way to see this is, so if I take a configuration which has an odd number of spin downs on the right side, it is impossible to find a configuration for the blue spins. So this means the green ones, they have to fulfill the property that the number of spin downs is an even number or 0. Intuitively, you can also understand this if you think about flipping one blue spin, then you're always flipping 2 green spins. So this is somehow the symmetry breaking. If you flip a blue one, you flip 2 green ones. So this means you can only have an even number of spin downs in the green ones. Now, out of this English sentence, you can actually make an energy simply by multiplying these. So if you multiply the spins and put a minus sign in front of it, you actually have an energy penalty if there is a violation of this constraint. Which means you can now do the following strategy. No? You can say, can I somehow map my original problem to a physical problem where I encode these constraints as energy penalties. So as I said, if you have a loop of 4, for example, let's say you take this loop here, and you make a 4-body interaction between these 4 qubits, then you have penalized an invalid solution. And now our exercise is we have to find, out of this all-to-all model, we have to find k minus n constraints. Actually, that's no problem because there's n factorial loops, so k minus n is, so to say, a small subset of them. And then we can say, let's add one additional condition. Let's say, if we, on a chip, realize these constraints, we want them all to be on a square lattice and nearest neighbor interactions. So there should be no long-range interactions left. And it turns out that this is actually possible, and there is only a single solution to that, or like up to symmetries. And the solution looks exactly like the one that I've shown here. So the main building block is that I take a loop of length 4, and I get 1 to the right, 2 to the left, 3 to the right, and 2 back. And here I've drawn the elements that I need here, so for 2, 3, 2, 4, 1, 3, 1, 4. And if I then go with this pattern through the whole system, I actually find a very regular structure in which I can satisfy this. Which means what comes out in the end is now a model where each qubit represents the parity of two logical qubits. I have four-body interactions among nearest neighbors. The layout is kind of a triangle made out of squares, so this triangle shape is important. And there's also a subtlety that here in this bottom row, I have free-body terms. So people that come from a lattice gauge background identify this as a lattice gauge model, where you have here a fixed boundary on one side and two open boundaries on this side, and you get this triangle. So this was the original parity transformation, which is already a few years old now, 10 years old. The outcome of this is that you can map an all-to-all spin model to a nearest neighbor model with four-body interactions. And the important thing is, as I said, pair interactions become single spin flips. So if I flip a spin, if I flip 1-3, it's like an interaction on 1-3, or a local field acting on this qubit would be like an interaction between 1 and 3. And so this is this was the starting point. And now we can ask ourselves, okay, this is now for spin models and so on, but can we make a quantum computer out of it? And this was, so to say, also already some time ago, where we introduced the universal version of that, which means we looked at, can we, in this logic of parity variables, can we make a universal quantum computer? And what is shown here in this paper is basically the standard way how we think about quantum computing and this dual version or this parity version of it. So let me just go through it. So what is on the very left is a gate set. So this will be a universal gate set. We have Rx, Rc, and a C-phase gate. So this will be a pair interaction, and these would be single qubit operations. Which means if I have a standard way of thinking about a quantum computer, I would have here my qubits sitting on, let's say, a square lattice. And in my notation with the lines and the rectangles, I have my single qubit operations would act on a single line. Or here, let's say they act on this qubit, which means they would only act on this qubit. If I have now a pair interaction between two qubits, then I've drawn this here that these qubits are not neighboring. If they're just neighboring, I just do the interaction. But if they're not neighbors, I have to do something. No, I have to do a surgery or have to do swap operations or anything like this. Now I have to transport information from here to here. And this is often super expensive. For example, if I do this with CNOT gates, I would have to do 3 CNOT gates per node or per link, which is indicated somehow here. Now, if I do the same thing in the parity picture, then a single qubit operation becomes, so this is the triangle that we've seen before. No, every qubit represents the parity. And if I want to do now, because I've more or less I got rid of the original qubits, if I want to do now a single qubit operation, I have to act on multiple qubits. So these lines that you see here, this will be CNOT gates that I have to act on a full line in the system. And this will be index 1, for example. If I want to flip index 2, I would have to do it on this line. 3 would be on this line, and 4 on this line, and so on. So we call this the hockey sticks. So single qubit operations become more expensive. Single qubit set operations are again as simple as before, because we looked at the parity in the set direction. And now the interesting thing is the pair interactions. The pair interactions become now single qubit operations. And so instead of putting qubits together and making a pair interaction, I can actually act with local fields or local operations on 3 qubits. And this is now something that I can also fully parallelize. So for example, I can, if I have an algorithm which has a lot of pair interactions, let's say all-to-all, I can act on all these qubits at the same time, and I've done all the pair interactions that I needed. So if I do the parity mapping, I get a trade-off. Single qubit operations become more difficult. Pair interactions become more or less for free. So I can ask myself, can I actually gain something from this? And the first thing that I want to show, and this is more like a side remark, if I want to do fault-tolerant quantum computing, so fully fault-tolerant quantum computing, then this is a very interesting starting point, because this is like a classical code that I can now combine with any other classic code in a CSS style. And in this code, the logical interactions are already there. They're already included. So if I want to do an operation between 2 and 4, I act on this single qubit here. What we've also shown is that, so this can be implemented in 2D, can be combined with any other one. It's fully universal, so as we've seen before, this is a fully universal code. The connectivity is independent of the hardware connectivity, so this is like the big plus, that I have only local interactions, but I can act on arbitrary long-range interactions in the logical picture, and I can fully parallelize this. And very recently, I would also like to mention that we have shown that one can optimally decode this problem, and the decoder is actually presented in this paper here. Okay, so this is just how errors work in this model, so you can, if you have errors, you can decode them. Now, let's think about how would I design now an algorithm in this parity picture. As I mentioned, if I have now pair interactions, I can actually act on single qubits. And this is the general logic, that I want to generate qubits which hold the parity information of multiple qubits and then do the interaction there. Which means in our picture, the computation or the design of an algorithm actually reduces to the question, can I design or generate these parity labels at single qubits? So in this triangle that I've shown, right, I basically generate all-to-all network. But if I have, let's say, free-body interactions or some interactions are missing, I would like to compile this. And so the logic or the way we design algorithms is really to think, can I put the parities that I need in an efficient way, or the parity labels that we need on certain qubits, do the operation, and then efficiently do the next one. And I will show you an example for an all-to-all network starting from this triangle. So here, if you just take what you see here, then this label generation is somehow, I would say, trivial, or the way I've shown it, but it has an overhead. It has an overhead in qubits, which makes it less attractive. So can we get rid of this overhead and still generate all these labels? And the way this works is the following. We take the triangle that we've just seen, and we take the second triangle and put it like a Möbius on top. So here we have label 1, 2, 3, 4, 4 in the colors, and these are all our parity variables. And now we make a second one just to make this somehow a rectangle and symmetric. So before it was a triangle, now I have a rectangle. And now I can look at a certain line in this Möbius strip. Let's take this one here, 2, 3, 1, 3, 1, 4, 0, 4, 0. If you know all these parities, you can actually reconstruct your logical qubits. So if you know 0 and you know 0, 4, you know 4. If you know 0 and 4, and you know 1, 4, you know 1. Then you know 3, and then you know 2. So you can decode from this line, you can decode your whole logical system. And now, surprisingly or interestingly, this is true for any line here in the system. So you can take any of these zigzag lines and you can always reconstruct the logical information. Intuitively, this is kind of clear because we made an overhead of n squared, and now we take n again out, which means it's somehow clear that this information must be in every line. And now we can ask ourselves, okay, if this is the case, then can I trade off space for time? Like in a Floquet code, can I trade off, instead of implementing n squared qubits, can I implement just n of them and go through the system in time? And it turns out, yes, I can do this with rather simple operations. So let's say you're in this line here, 2, 3, 1, 3, 1, 4, 0, 4, 0. And you want to go to the next line, which will be 2, 3, 2, 4, 1, 4, 1, 0. So you basically flip the zigzag. Then you can do this with two CNOT gates, no? Because this was originally a 4-body, which means if you want to go from here to here, you just execute these two CNOT gates here. And you can do this next one for the next plaquette, and you can do this for the other plaquettes, and if you follow this, you actually get this pattern. So you moved your indices from this line to this line here. So you went from here to here. And this means this is now a recipe how you can generate every parity label, and if you're in your algorithm at this label, you just execute a single qubit operation on it, and it's like you did in the logical system, the pair interaction between 2, 3. And so, yeah, so you go through the system like this, and with this generate all parity labels. And now let's apply this and see if this actually helps, no? Because so far we've just, modeled things around, so maybe there's a trade-off, one thing is better than the other, and so on. So let's look at an example, and we did this for the Fourier transform. So this is textbook Fourier transform, which requires all-to-all C-phase operations. And now we can, so to say, implement this in this parity language. And I don't want to go in detail of all of this, but I would like to show you a few highlights of this. So first of all, what you see is that the logic that I said, no, so the pair interactions we only use to do the logistics of our quantum information, right? So with this, we are transversing through this parity triangle. And then in between you do these logical rotations, so some of them are Clifford, some of them are not. And by doing this, you execute all the gates that you need. So as I said, the logic is generate parity variables or labels, do logical operations on them, and this replaces your pair interactions. And the second thing that I would like to highlight is the way we visualize this. So usually if you draw a gate model, you don't draw these parity labels, right? So here we start with 0, 1, 2, 3, 4, and then at some point you have here 1, 2, 1, 3, 3, 4, and so on. And we also have this color, no? You see, for example, the information about the logical qubit 0 somehow goes through the system like this, no? So the red color goes like this. So here in the middle, it's somehow in the parity hidden. The yellow one goes like this, and so on. So every of these qubits has its information. And this is what we call the parity labels. And as I said, this is our main tool for designing quantum algorithms. So instead of thinking about you have logical qubits, they have interactions, and then you have to move them around, we are completely delocalizing our information, and we just keep track of it. So we, in every step, we keep track of where is the quantum information positioned. And we call this the parity labels. And here in this picture, which serves as a visualization, see this with the colors. We have also formalized this to a large extent, and also with a real formalism behind it. This is this paper here, which introduces this parity flow formalism. And the idea is really the following, that we have, so the blue and the red labels here are X and C information about qubits. And these lines that we typically associate with qubits, they are literally just containers. And these containers, they contain now information from different qubits. And this is the actual thing that we are interested in, because we are not doing then the gates, we are actually acting with single qubit operations on them. So this means if we, if we look at this line here and we do some gate, it would act on the parity 1, 2, which is equivalent to an interaction between 1 and 2. So this is actually a way how you can add, how you can deal with this whole parity formalism, and if you're interested in this, this is the paper to it. So now let's look at the outcome, the thing that we've seen here. You can still say, oh, nice, but what's the thing? Yeah, the thing is that this is actually the most efficient way how you can implement the quantum Fourier transform. And there is the previous milestone in this is actually already a long time ago, and I saw that Austin Fowler is also here. So he has I think it's a 2004 paper with a 2024 update, which actually introduced a nearest neighbor version of the Fourier transform. And this was, so to say, the best implementation for the quantum Fourier transform with nearest neighbors. And there were two variations of this, by Holmes and by Park, rather recently, where they optimized for gate count and where they optimized for depth further. And the remarkable outcome of our work is that we actually achieve or the outcome of these papers was that either you can optimize for gate count or you can optimize for depth. So as you can see, in this version you have less CNOT gates, you have n squared instead of 3½ n squared, while the depth is, so to say, quadratic here, while here it's linear. And what we have achieved is to actually optimize for both, so the CNOT count and the depth at the same time. So this here is really a new version of the Fourier transform, which beats all the previous attempts, in this case on a linear chain without overhead in the qubits. Now, this is the scalings. So if you look at the CNOT depth, then you can see that the red curve is, so to say, the one that we've just seen. Then there's these two references, which are, so to say, these two curves. And one thing that I find personally the most remarkable outcome of this is that in this parity picture, we actually get the same CNOT depth for a nearest neighbor linear chain as we get in a system with all-to-all connectivity on a physical device. So this, I think, is really also technologically remarkable, because it somehow shows that by this parity mapping, you can achieve the same CNOT depth with a linear nearest neighbor chain as with an all-to-all connected physical system. I think that's quite a remarkable outcome of this, and I think very interesting for all 2D platforms. Okay, now one step further. This was for linear chain. Now let's look at other geometries. Let's look at square lattices and higher order terms. As I said, our idea is to generate these parity labels. And we do this in two forms. We are kind of abusing the actual gates of the algorithm, like the CNOT gate, by doing this. So for example, if you look at the CNOT gate, what it actually does is, if you have your labels here, it changes the labels. And if you do a so-called double CNOT, it not just changes the labels, but it also flips them. And with this, you can, at the same time, move your information around and also do the operations. And to just quickly show this, if you, start with these two operations, so the double CNOT and the CNOT, so this would be our ISA, so to say, you can construct what we call the Parity Twine, which is a backbone. The backbone consists of these double CNOTs, and the legs, which are standing out here, which are the CNOT gates. And this actually allows you to go from purely 1D to something that's a little bit more than 2D. And by doing so, we can actually further decrease the CNOT count and the depth. And this is remarkable because there was even the conjecture, which is not so long time ago, 2022, that it's impossible to reach an advantage over the linear chain with having a square lattice. And actually with this Twine method, we have shown this, that by increasing the connectivity, you can gain something. And I will just finalize this a bit. So this is somehow the summary of the Twine method. So this is this paper here. Christoph Leckenstein, who is the main author of this, is also here in the audience. What we are showing here is the average gate count for, in this case, all-to-all a problem. And the red dots are the previously best known implementations of them. And what we have achieved is that with this parity method, in particular this Parity Twine method, we were able to reduce this average gate count for every connectivity. So for the linear chain, for the heavy hex, for the ladder, for the square grid, and even for the all-to-all model. And so to say, these are the tables to it, so you can see that we've reduced count and depth for all these geometries. So this is the world record implementation of QFT on all geometries. I would also like to just show some hardware realizations. So this is because number of qubits, number of gates, and so on is, of course, a super important thing. This is on an IQM device, but it's called IBM process fidelity. The reason is that this, for the Fourier transform, there's an IBM paper where they looked at the process fidelity, which is the actual final fidelity after the whole algorithm. And this is the number of qubits. And what you see here is the Twine ladder. So this is really making use of the square lattice with the backbone and the legs. This is the linear version, and here this is called Fowler, so to say, as appreciation of the 2004 paper, which is, so to say, this curve. And what you can see is that even at already relatively small numbers, you already get this rather strong improvement in the fidelity. As I said, qubit number and gate number, of course, all go exponentially in these final fidelities. So I think, we're very proud about this improvement. There's even, so to say, larger hardware. So on the IBM Heron device, we also did the same experiments. So in this case, you can go up to 50 qubits. Again, working together with people at IBM, we looked at this process fidelity. And again, what you see is using this Twine method here, in this case, this was a heavy hex version, and on a linear chain, you can improve the state of the art by several orders of magnitude. So this, I think, is a quite remarkable result, and something that shows that this parity mapping really is a new tool to implement quantum algorithms. As a last point, I would like to mention that what we've shown here was for rather specific examples. What people at FZ Jülich did was they've taken their compiler and they've added these Parity Twines to the compiler. And so this was done in May. I think our paper came out beginning of the year, so in a few months this was already possible. And what they see is that by adding this Parity Twine network, as they call it, they got for general compilation of problems. Compared to swap networks, they get a reduction in the depth of 85% and 28% reduction in the gate count. So I think also quite a remarkable improvement. So with this I would like to finish. So the Parity architecture is like a real, I think, different paradigm. We think about generating parity labels, acting with single qubit operations. The redundancy in the encoding is already from the beginning, so we are starting with error-corrected code. It's a classical code, so it can be combined with any other code in a CSS style. And we have shown the world records in the synthesis of things like quantum Fourier transform, which are, of course, super important algorithms. And this is the team at ParityQC. And as said, some of the people who did the work are also here at the meeting. So with this, I would like to thank you.
Thank you, Wolfgang.